Thank you, Paul. Good afternoon, everybody. So as Paul has said, this talk is going to focus on system requirements definition, and I'm going to introduce some principles, and then Marek is going to pick up and go into a little bit more detail. And in terms of where do system requirements fit, I'm trying to show that on this simple diagram here. So in our first seminar, so that's to the left of this chart that you can see on the screen at the moment, if you can think of it in that way. In our first seminar, we covered some principles of satellite navigation and related navigation systems, and went through some of the threats and vulnerabilities that you might expect to experience. So the logic flow here is as shown on the screen. So if you can then define the requirements of your system, it gives you a baseline against which to assess risks. And having assessed the risks, you can start to think about how to build a system. And often that's talked about as a system of systems to achieve resilience. Or another way of looking at it can be a layered approach. So you put different layers together to give you the performance that you require. So today's talk is the left-hand one, system requirements, or today's talks. The middle one is our third seminar that Paul mentioned. And the right-hand one, we're going to start talking about that in the fourth seminar, and then hopefully there'll be some other events going on later in the year. So hopefully that positions what we're talking about today in a picture. So how do you define requirements? Well, it's a huge topic, and I'm going to just touch the surface, and Marek's going to go a little bit below the surface and go into a little bit more detail. But what you see on the screen here is what PNT people call the required navigation performance, RNP. If you want to find more out about this, it's worth going into your search engine and tapping in Navipedia. There's more information, but at a basic level, really all navigation systems requirements should include a measure of these four parameters: accuracy, availability, continuity, and integrity. In terms of their definitions, what I've done here is to try and summarize an already short definition, which is a very dangerous thing to do. But I hope you'll get the gist from what I've written here. There is, again, more detail available on Navipedia. Accuracy is a measure of the reported versus the true position. And accuracy would normally, if you've watched the first talk, would normally be shown in terms of a mean or a root sum of squares type accuracy, averaged over a period of time. Integrity is an indication of trust. And in particular, if you've got a system with high integrity, you can expect timely warnings of any issues. For example, there could be some limits set, and if those limits are breached in a particular area, then you might get an integrity flag, which might get more severe as the range of the limits is further breached. Availability is normally shown as a percentage and is defined as the percentage of time that the position, navigation, or time, the position or time is reported. And continuity is the probability that the system performance will be maintained to stated accuracy without interruption. So in no way am I suggesting that these four parameters are a complete definition of a system performance, but I would suggest that they are required as a minimum set in any positioning navigation system requirement definition. So let's look first of all at a GPS receiver, just to illustrate this a little bit. So in this example, I'm talking about an autonomous GPS receiver. And the color coding here is indicative. So red would indicate low, orange would indicate medium, and green would indicate high. So what I'm suggesting on this chart is that for a run-of-the-mill GPS or even GNSS receiver, accuracy typically is rather good. Now, obviously, your definition of accuracy depends on your particular requirement. But if we just speak in general terms here, in fact, I'll speak in fairly general terms throughout the whole of my little talk. Accuracy of 3, 4, 5 meters for a single frequency GPS system anywhere in the world autonomously, I'd say that's pretty green. On the other hand, with a standalone GPS or GNSS system on the left-hand side, the integrity is pretty poor. So there are all sorts of software fixes and so on that we'll talk about in subsequent presentations. But at a very basic level, your GPS will give you a position and time if you're interested in time, but often won't tell you the integrity or the goodness, if you like, of that position, and it will not tend to raise flags if there's an issue with the accuracy. Continuity is also relatively poor, particularly if you're in a built-up area. And we saw in the first seminar that as you move indoors, for example, or as you go through very high buildings, you can sometimes go below 4 satellites that are required to continuously report position and time. And availability is somewhere in the middle. It normally works, right? So your GPS receiver would normally work, but there will be periods where it may not be available either for a system issue, you might be jammed, or there may be some other problem. So it doesn't take much of a leap to figure out that very few applications indicate autonomous GNSS as being sufficient. Nearly always you have the autonomous GPS or GNSS receiver coupled with other systems to give you a level of performance that you need. And Marek, in his talk after mine, we'll talk about the different layers or the different levels of requirement. For example, the receiver, the system, the application. But here and in the next chart, I'm just talking about a receiver. In fact, if I move on to the next chart, so you can see the top left of the chart here. There is the standalone GPS receiver that we just covered with its relatively poor integrity and continuity, but quite good accuracy. And I talked about coupling GPS with other devices. Well, in this example on this chart, in the bottom left is an indicative performance of an inertial system. So typically, inertial systems have good accuracy, but for a shortish period of time. Their errors accumulate over time. So that's why I've shown accuracy of the inertial system in the bottom left here as being relatively poor. But inertial systems continuously work, typically. Their integrity is normally good, and continuity and availability also good. And you can see that if you add the strengths and weaknesses of these two modules together, you get a better performance overall, typically, than you would from one of the systems in isolation. So that's some of the thinking that will sort of underpin and underlie what I've got coming up in the next few charts, and then what Marek will go on to talk about. That system performance is often system performance requirements are often more challenging than you can get from a single module, but combining them together allows you to build up a performance envelope that will meet the system requirements. Okay, so let's try and bring that into some examples. So we've just been talking about receivers and inertial elements, but let's flip now to more system level. So let's think about ships and smartphones and autonomous cars. And I'll just walk through these one by one in the next couple of sections. So if I could invite you, first of all, let's think about a ship out of sight of land. So out in the middle of the sea, out of sight of land, and just spend a minute or so just thinking through what color coding you'd give to accuracy, availability, continuity, and integrity in that example. So I would suggest it's something like this. And so a ship out of sight of land doesn't really need particularly good accuracy. A few hundred meters, even a nautical mile, is typically fine if you're well away from land. And you don't need availability and continuity particularly. In fact, if you think back to days gone by when mariners were reliant on celestial navigation using handheld instruments and sextants, maybe a fix every 30 minutes or every hour, maybe even less. But what you do need is some degree of integrity. You need some confidence that the position that you are relying on, even though you might not need it very often, can be relied on, even though it might not be particularly accurate. You don't want it to be particularly inaccurate. So that is how I would use this tool for a ship, the example of a ship out of sight of land. If you think then about a ship or a vessel near to the land, it's a very different situation. And this is contextual requirements and much more challenging. And well, indeed, there are many different ways that ships augment GPS when they are close to land, not least of which the tool that mariners would call, I think they call it the Mark I eyeball. So looking out of the window, in other words, or maybe using differential corrections and other positioning tools and techniques. So there are a couple of examples with respect to ships. And if we move on now to a smartphone, well, very complex device, actually, a smartphone. And I put this one up because I think it's got quite an unusual requirements envelope. And one of the key factors here is that for designers of smartphones, safety is not normally the consideration in defining the requirements. So that's why the accuracy is, I would suggest, a bit lower than in many other applications. And the integrity it is somewhat important. It's kind of useful information, but it's not critical information. And continuity is less important. So it's convenient to have a location all the time from your smartphone, but many of us will have seen occasions when we may not have had a reliable position. And availability, though, is important to have a position available a good percentage of the time. So in terms of the smartphone as a system, it's really using sensor fusion to deliver this performance. And that high availability means that if one sensor is not available or is not available to a good specification, the phone will use intelligent algorithms to build a situation where you get a position, even though it might not be quite as accurate. And the phones I know use different algorithms for different use cases. So the way that they blend the different signals of opportunity that that build to a position report do vary depending on whether the phone's in your hand or up by your ear or in a car. So really quite sophisticated use of sensor fusion algorithms in the phones. And just to unpick that a little bit, I'll just run through a couple of example charts here. So you'll have seen this all the time, the blue dot. And the example on the right, this particular phone, I think it's a GPS and GLONASS L1 device. And there's a very good position fix on the right, clear sky and good visibility of the satellites, low dilution of precision. And that's why you've got that blue dot with very tight resolution. On the left, you can see a slight fuzziness around the blue dot. And that's because when I took this particular screenshot, I had moved closer to a multi-story building. So although I was still getting a position fix from the satellites, the confidence in that position was weaker because effectively half of the sky was blocked by the building. And the DOP, if you watched the first talk we gave last week, the DOP, dilution of precision, was higher, and hence you can multiply the DOP by the accuracy. And if the DOP was 2, for example, the accuracy would be half as good. So, but both of these are examples of position fixes using the satellite navigation sensors in the smartphone. And if you then switch to a mode or switch to a position where the GPS GNSS is denied, you might see that blue dot expand just that much further. And that's because the phone can't rely on satellite navigation anymore. And what you're seeing with this sort of accuracy, about 20, 30, 40, 50 meters, 20 to 50, tens of meters of inaccuracy at the moment, is Wi-Fi positioning. So the phone is getting a position by measuring the received signal strength from one or more, ideally multiple, Wi-Fi access points that are geolocated through crowdsourced information, and deriving a position with a level of uncertainty indicated by that blue dot. Wi-Fi positioning is an interesting topic, actually, and I won't go into detail, but there are some big improvements coming where Wi-Fi positioning will actually measure the round trip time rather than just the power level from the different access points. And that can bring this inaccuracy much tighter, perhaps in the next 3 to 5 years, I think. If we then, third and final leg of this little experiment, if we then turn off the Wi-Fi, you can see that is turned off on the left, indicated by that little Wi-Fi with a line through it. So I've got no GPS, no GNSS, no Wi-Fi. This particular phone doesn't have Bluetooth positioning. Some phones do, this particular one doesn't. And you can see that that blue dot has expanded even further. But you're still getting a position, so that availability is still good, such that when an app pings the operating system for a position report, the phone will deliver one, even though its confidence in that position may not be particularly high. And cellular positioning works today in a fairly similar way to Wi-Fi positioning by looking at the signal level to the nearest base station or base stations, and then estimating the position from that. And phones are quite clever. They'll also integrate that with the most recent high confidence position, which I think is why the actual location of the blue dot here is pretty accurate. It is actually where I was when I took this screenshot. But if you don't have that information available, the accuracy would be somewhere, the confidence would be somewhere within that, maybe a few hundred meters. And similarly to Wi-Fi positioning, cellular positioning is also improving as we move into next generations of cellular base station technology. There'll be higher density of base stations, which is a good thing from a positioning perspective, but also the round trip time will start to be measured more often. Yeah, so quite a lot going on there. Interestingly, based on that little flow that you've just seen, if you jam or try to jam a mobile phone with a GPS jammer, just a typical off-the-shelf Android or Apple operating system phone, it will continue to report a position almost always, because although you've denied and wiped out the GNSS, even multi-frequency GNSS, if you've got a multi-frequency GNSS jammer, you'll wipe out the GPS, but the phone will still report a position, typically based on Wi-Fi or cellular position. So it's quite resilient, even though it's not particularly accurate. If, of course, your jammer includes cellular frequencies and Wi-Fi frequencies as well, it would be quite an expensive jammer to do that, because they span from sort of 1 gigahertz up to 2.4, 2.5 gigahertz, so very broadband multi-antenna type jammer, quite expensive. Well, then there's nothing you can do about that. But it's actually quite difficult to deny the position on a smartphone completely for those sorts of reasons. Another example I just want to cover at a high level is driverless cars. Well, totally different situation to the phone navigation. In fact, more akin to a ship close to shore or in harbour, where the relative position is as important as the absolute position. And I would suggest all of these performance parameters are very important to be accurate and give you high confidence in the position. So actually very difficult to achieve. And I very briefly showed this chart in my first talk in the last seminar. And I thought I'd put it up again, because I think it only put in a very brief appearance last time. But this chart is indicative of what you might need for an autonomous car system turning left through a busy intersection. So certainly lane level positioning, safety critical, so high integrity, high availability, and continuity critical to the overall system performance. And of course, one other thing here, yep. So it's not just the positioning performance in terms of the positioning sensors that you need to consider in a system such as an autonomous car system. It's also important to consider the requirements of the non-positioning elements. And I've got one example on this chart, namely the accuracy of the mapping information. And then I've got a couple more examples on the next chart. So in this example, I think this one also put in a brief appearance last time, but let's just talk to it a little bit more. When you get down to lane levels of accuracy in an absolute positioning sense, then the mapping accuracy can become a limiting factor. And you can see that in this very simple couple of examples here. So on the left-hand side, the position of Church Lane going from up and down vertically on the left-hand side here is clearly not in the middle of the road, and neither is the more main road at the bottom here. And on the right-hand side, I don't know if you can see that clearly, but the Gulliman's Way, I think it's called, as that curves round, it's shown to be a smooth curve and then a smooth road, but the underlying reality is the road's got quite a kink in it. In fact, the road on the map actually seems to go across somebody's front lawn. So I mention this because it's important in considering the requirements of the system, because it may be that relative positioning accuracy, that there comes a point when relative positioning accuracy is as important or more important than absolute positioning accuracy. And then really moving into my last couple of charts here, there are many other factors to consider in complex systems, and we've all seen multiple diagrams like this, the connected autonomous vehicle, where vehicles not only know where they are in absolute terms, but also relatively to other vehicles, to other infrastructure, and where they are on their journey. So communications becomes very intrinsic to a system such as this. Timing and synchronization requirements, not only for cellular, but also for Wi-Fi and other communications infrastructure, becomes very important as part of a requirements definition. And standards start to come into play as well. So standards for safety, for example, and standards for communication reliability. And that brings in a whole other set of requirements for things like certification. So I suppose in summary, the requirements definition is simple at a basic level, but as you start to move into system and application level, there are multiple levels that are worth considering and defining. And I know that Marek will go into more detail on those in a minute. If you would like more information and you want to browse a little bit, particularly in terms of those guidelines and standards, you can see indicated at the bottom of the page here. We have got on the Institute's website links to a number of available receiver, system, and application standards. And it's a very deep and complex subject because there are such a vast number of applications that are enabled by positioning, navigation, and indeed timing. So with that, I shall conclude my remarks and hand back to Paul. Thank you very much.